Hello everyone, welcome to question session 1 for fluid mechanics. So first we will start with a slight revision on our part regarding your fluid properties and some basic concepts. Okay, so let's start with your continuum. Concept of continuum we know. So continuum is valid when your Knudsen number represented by Kn is equal to your mean free path upon the system dimension. Okay, so this lambda is your mean free path and this L is your system dimension system dimension, and your continuum is valid when your Kn is less than 0.01. This is the important point. Okay, continuum. Okay, so Knudsen number is less than 0.01, only then is your continuum valid. Okay, okay. So now there are slight few properties of your fluid which we have discussed in our lecture. So let's start with them. So first property is your mass density. Mass density. Second property is your specific weight. Specific weight or weight density. Weight density. Okay. Third property is your specific gravity. Specific gravity. Next property is your compressibility. Compressibility, or we can also say or bulk modulus. Bulk modulus. Okay. Fifth property we can talk about is, let me write it here. Fifth property is your Mach number. Mach number. Okay. Now next property is your viscosity or dynamic viscosity. Dynamic viscosity. Next, seventh is your kinematic viscosity. Okay, and okay, so let's start with this. So first I mentioned is mass density. So mass density is represented by rho, and this is your mass per unit volume. Okay, and its unit is your kg per meter cube or gram per centimeter cube. Okay, next specific weight is represented by W, and this is your weight upon volume. Okay, and is also equal to rho times of G. Okay, and unit is Newton per meter cube. Okay, specific gravity is your represented by S, and this is your density of fluid upon density of standard fluid. Okay, in case of liquid, your standard fluid is water having density of 1000 kg per meter cube, and in case of your air, your standard fluid is in case of gases, your standard fluid is air, which have the density of 1.2 kg per meter cube. Now, if you talk about compressibility, then compressibility is the ability of the fluid to be compressed. Okay, and this compressibility is our inverse of bulk modulus. Okay, and if we talk about bulk modulus, then bulk modulus is defined as dp upon dV by dV, change in volume, change in pressure upon change in volume. Okay, or change in direct change in pressure upon volumetric strain. Okay, so this can be also written as your dP upon volumetric strain can be represented in terms of density by d rho by rho. Okay, and this K, this K, like compressibility is represented by beta, and bulk modulus is represented by K. Okay, compressibility beta or bulk modulus. Okay. Okay, and in case of bulk modulus, of course the bulk modulus have a unit of bulk modulus. K has unit of your Pascal or megapascal, same as pressure. Okay, and if you talk about bulk modulus, there are two type of bulk modulus: K adiabatic. Adiabatic bulk modulus is your gamma times of pressure, and K isothermal. Isothermal bulk modulus is equal to your pressure. Okay, so these bulk modulus values are for adiabatic and isothermal respectively, such as asked in the question. Okay, and one more thing we can say from here, that K, of course we can say that K, your adiabatic is greater than that of K isothermal. Okay, and similarly we can say that that compressibility of adiabatic is less than that of compressibility of isothermal. Okay, so from here we can write a statement: isothermal compression is easier. Isothermal compression is easier. Okay, now let's talk about the next property, that is Mach number. So your Mach number is defined as your velocity of fluid upon speed of sound. Velocity of fluid divided by speed of sound, of course in the same medium, in medium. Okay, now your C value for solid is basically, or in like in case of let's say in fluids, in case of fluid not fluid, in case of liquid it is uh, or we can say fluids, sorry. See, in case of fluid is given by C is equal to root of K by rho, or basically in solid also the same is given, but instead of K, there we use modulus of elasticity E. Okay, now in case of isothermal or adiabatic we can talk in two cases. Okay, so this is, let's say, isothermal, and here adiabatic. So for isothermal we can write C is equal to root of P by rho, and adiabatic we can write C is equal to root of gamma RT. Okay, next if we talk about dynamic viscosity, so your dynamic viscosity or viscosity is basically internal resistance of the fluid. Okay, so in dynamic viscosity we studied that tau is equal to this is your Newton's law of viscosity. In dynamic viscosity we studied your Newton's law of viscosity. Newton's law of viscosity, and this law states that your shear stress is directly proportional to your rate of strain. Okay, and is given by mu du by dy. Okay, and in case of linearization, if you want to linearize the solution, so we can write tau is equal to mu V by H. And this linearization is generally done when your film thickness or H is very small, very small. Only then this is done. Okay, your kinematic viscosity is dynamic viscosity is your mu, and kinematic viscosity is denoted by nu, and this is basically your dynamic viscosity upon density. Okay. Now, if we talk about units of dynamic and kinematic viscosity, so let's talk about dynamic viscosity, and then we will also talk about your kinematic viscosity. Okay, and let's start. So, for dynamic viscosity, we use Pascal second, or we can use Newton second per meter square, or we also use your kg per meter second, kg per meter second, or poise. This is your CGS unit, okay. And this poise is your gram per centimeter second, okay. And in case of kinematic viscosity, we use meter square per second, okay, or centimeter square per second. And this is also your Stokes, written as Stokes, okay. And if we talk about conversion from CGS unit, of course this is your CGS unit, okay. And if I talk about conversion from SI to CGS, so your 1 Pascal second is equal to 10 poise. Okay, 1 Pascal second is equal to 10 poise, and 1 meter square per second is equal to 10 to the power 4 Stokes. Okay, so this is your relation from SI to conversion from SI to CGS unit in case of your viscosities. Now, if I have also talked in this about your variation of dynamic and kinematic viscosity for liquid and gases with respect to both temperature and pressure. So let me do it here. So let's say that. So now, if we talk about pressure and temperature, so let's talk about the pressure variation. Pressure, and this is temperature. Okay, so pressure will increase when and temperature will increase in case of following. When we increase the pressure, what will happen in case of the liquid and gases, and when we increase temperature, what will happen to viscosities in liquid and gases. Okay, so when we increase the pressure, on increasing the pressure, your in liquids you have no variation for both dynamic and kinematic viscosity. In case of gases, you have no variation for dynamic viscosity, but your kinematic viscosity decreases. And why is this? Because generally your your dynamic viscosity for gases is directly proportional to square root of T, okay, and dynamic viscosity of gases is directly proportional to T की power 3/2, and your density of gas is directly proportional to pressure, okay, and is also inversely proportional to temperature, or okay. So if we use this here, like mu is equal to nu is equal to mu upon rho, so this becomes 3/2. We can get the relation from here, okay. Okay, now if we increase the temperature, then due to increasing temperature, the viscosity of liquid decreases, and it's true for both the viscosities, okay. And in case of gases, increasing the temperature, as we can see here, both values increases, are directly proportional to temperature, okay. So I hope you understood this. Now, so next point is vapor pressure. Vapor pressure. Okay, so vapor pressure is your, like as I mentioned in the class, is the pressure on the, like on any surface or on the fluid due to the vapors of that particular fluid. Okay, so this is generally printed by your PVS. Okay, and when we increase that, with increase in temperature, your vapor pressure increases. Okay, and Hg, that is has your mercury has least vapor pressure, least vapor pressure due to strong cohesive bond, strong cohesive bond. Okay, this is the reason why your mercury is generally used in your thermometers. Okay, now due to this vapor pressure, a new type of uh, like uh, like if you talk about the consequences of vapor pressure, so there is a cavitation. This is a phenomenon, cavitation. Okay, so cavitation is a phenomenon occurs due to your vapor pressure. Okay, whenever your minimum pressure, in the system is less than that of your vapor pressure, in that case what will happen? When your minimum pressure is less than that of vapor pressure, your liquid will start to boil. Boiling will start. What else? Now after the liquid start boiling, so whenever it will like bubbles will start to form, and due to the formation of bubbles, when these bubbles will move in high pressure region again, in that region what will happen? Bubbles will and bubbles will form. Let me write here. Will form. Okay, so and now bubbles will collapse in high pressure region, high pressure region region. Okay, causing like okay, high pressure region. Okay, and like whenever they collapse, if they strike the wall, of the pipe, the wall, then it will cause remove the material removal from the pipe wall. Okay, and this phenomenon is called as your cavitation. Okay, now talking about the next property, that is also important one property, that is your surface tension. Surface tension. Okay, so this surface tension is represented by your sigma, and this is due to unbalanced force, unbalanced force. Okay, and with increase in temperature, your surface tension decreases. Okay, at critical point, at critical point, your surface tension is equal to 0. Okay, and this surface tension is a binary property, binary property means that it is dependent on your like two type of surfaces, two type of interfaces. Okay, two type of fluids must be in interaction to occur your surface tension. Okay, now if we talk about like your detergents, then detergents cause detergents, if you mix detergent in the water, then surface tension decreases. Okay, or let me write causes or reduces surface tension, reduces sigma. Okay, sigma decreases. Okay, now of course If we talk about numerical form, as I mentioned earlier, sigma is equal to your F upon L, okay. And also, like if you talk about the unit, this is your force per unit length, so unit is your Newton per meter, okay. And this length in like we also use it as like length or perimeter, we also say it, okay. Like length of contact of the solid with the liquid interface, okay. And if you talk about surface energy, then surface energy is equal to your sigma into change in area, change in area. This is your total change in area is your surface energy, okay. And in case of your movable wire, we know that we generally use your surface tension force into delta X, and surface tension like your surface tension will be on both side of the wire, okay. Like if this is the wire, then on this surface, both surface, there will be certain surface tension, okay. So this is the important relation. Sigma into change in area is your surface energy, okay. And of course this is in joule. Next, due to this surface tension, the new type of phenomenon occurs, which is your capillarity. So let's talk about capillarity. But before that, let's discuss your surface tension application. Okay, so there are a few famous applications. First one is your water droplet. Water droplet. Okay. Second one is your let's talk about air bubble in water. Bubble in water. Okay. Next, if we talk about, then let's talk about bubble or soap bubble. Okay. And last is your jet formation or water jet or liquid jet, let's say liquid jet. Okay. So in case of or let me write a relation before. So your Pi inside minus P outside of any curved surface is given by 1 sigma, or it is also like is 2 sigma times of 1 by R1 plus 1 by R2, okay. So this is the relation, okay. And in case of your water droplet, it is your one interface, okay. One interface, okay. And your delta P is given by delta P, like Pi minus P naught is equal to like your this will be 1 by R1 plus 1 by R, both will be R1 is equal to R2 is equal to R in case of your water droplet. So this become 4 sigma by D, 4 sigma by D, okay. Okay. In case of your air bubble, in the water, this will be like similar condition as to of water droplet, and here also delta P is equal to 4 sigma by D, because this is also a single one interface system, okay. This is also an one interface, okay. This soap bubble is your two interface system. Two interface in case of your 2 sigma is in case of your 2 interface, and 1 sigma in your one interface system, okay. So delta P here is your 8 sigma by D, okay. Now this if we talk about liquid jet, then liquid jet your R1 is equal to R and R2 is equal to your infinity, because it is like a straight line, something like this, okay. So if we substitute this, so we will obtain delta P is equal to 2 sigma by D, okay, because it is a single interface system. Okay, 2 sigma by d. Okay, so these are your some like your application of surface tension. Okay, and now if we talk about capillarity, okay, like if you install a, as I mentioned earlier, uh, like a tube, a small, very small diameter tube inside a liquid, then due to surface tension, the liquid level will either rise or either fall. Okay, so in capillarity, either there can be like capillary rise, okay, or can be capillary fall. Okay, so capillary rise is due to adhesion. Okay, let me write. Due to adhesion. Adhesion is your force of interaction between like different two different type of molecules. Okay, and cohesion is between same type of molecules. Okay, so in capillary we have different cases. Okay, we basically balance the weight of the liquid in the column with your weight with your surface tension force. Okay, and we obtain different formulas. So let me directly write formulas here. That is 2 sigma or 4 sigma cos theta upon rho g d. Okay, and we also obtain 4 sigma cos theta upon rho g times of d naught minus di. Okay, we also use t sigma cos theta upon your rho g times of t. Okay, and these different formulas are used in different conditions. Let me mention them here. So this particular formula is used in case of your uh, tube of dia d, tube of dia d. This one for annular tube. Okay, this one for parallel plates. Okay, and one more thing I would like to mention it here, that is your variation of pressure inside a capillary tube. Okay, so let's say that here we have a capillary tube. Okay, so let me make it look good for you. Okay, so let's say this is your tube. Okay, and we have of course a container inside which the tube is kept. Okay, so let's say that this is your container. Okay, and there is some certain liquid filled inside this. Sorry. Okay, so let's say it's up to this surface. Okay, now of course the liquid will, let's say that this is water, so liquid will rise up to certain point. Let's say it rise up to this point. Okay, it rises to this point. Okay, so now I will rename few points here. So let's say this is your point number 1, this is your point number 2, this is your point number 3, this is your point number 4. Okay, so point number 4. Okay, so if I want to draw the distribution of pressure inside this, so let me draw it here. Okay, and this is the interface. Okay, so at point 1 and 2, so P1 is equal to P2 will be equal to your P atmospheric. Okay, so here the pressure will be this level, like your pressure will be P atm. P atm. Okay, now since we are moving upward inside a liquid column, so your pressure will start to decrease. Okay, and it will reach some pressure here. This is the final pressure at point 3. Okay, okay, so like this is for point 1 comma 2, this is for point 3. Okay, and if we talk about your point 4, then after that point what will happen, like this point 4 is open to the atmosphere, so here the pressure again will reach P atm. Okay, this is again P atm, and above that the pressure will remain constant. Okay, like this. Okay, so this is point number 4. Okay, so this is your pressure variation. So below the minuscule of the capillary tube, we have pressure less than that of atmospheric pressure. So if we drill a hole at this point, so what will happen, outside air will be sucked inside, and this liquid level will quickly fall to the bottom. Okay, so we are done with this part. Next part, rheology. So in rheology, we studied about your Ostwald equation. Ostwald equation. Okay. So what does your Ostwald equation say? It tells us that your shear stress is equal to 8 times of du by dy to the power n plus a constant, that is b. Okay, and your apparent viscosity, and there is like this term a, or we can also write it as, let me write it as eta times of du by dy plus b, and this eta is your apparent viscosity, apparent viscosity. Okay, and this value of this eta is equal to a times of du by dy to the power n minus 1. Okay, so yeah, so for the various fluid, if we study the behavior of the shear stress and strain rate, so let me draw them here. So they are different fluid as I mentioned earlier, so let me draw them here. So first one, this is your Newtonian fluid. This is your Newtonian fluid. Okay, and for Newtonian fluids, your n is equal to 1. N is equal to 1. Okay, and this here represent your pseudoplastics. Pseudoplastics. Okay, and for pseudoplastic your n is less than that of 1, less than 1. Okay, this line here represent your dilatant fluid, and for dilatant fluid your n is greater than 1. Okay, and as I mentioned earlier, that the equation, there is also constant term here b, which is used for your Bingham plastic end. So let me move it downward. Okay, so let's keep it here. This is your Bingham plastics. Bingham plastic, and Bingham plastic has also our n is equal to 1. Okay, there are now these are your basically time independent. Okay, you're like there, as I mentioned earlier in the class, that there are two type of viscosities, as I mentioned, fluid, sorry, in rheology, time dependent and time independent. Okay, so these are time independent. Now there are two fluids which are time dependent, so let me also show them here. So first, this is your thixotropic, thixotropic, and thixotropic has N less than 1. Okay, and this is your rheopectic, rheopectic does have your N greater than 1. Okay, and this the gap here is your basically this constant B which I have mentioned earlier. Okay, now there are two more type of things we can mention, like this line here represent your ideal fluid, this is for your ideal fluid. Okay, so even in the absence of your shear stress, even the slightest shear stress is tried to be applied, then there will be presence of shear strain. Okay, and this line here will represent your ideal solids. Okay, solid, no matter how much shear stress you apply, there won't be any shear strain. Ideal solids. Now for each one of them we will see some example. Okay, so let's start with the first one. That is, let's start with dilatant. Dilatant fluids. Okay, so these dilatant fluids are also known as your shear thickening fluid. Shear thickening fluid. Shear thickening fluids. What does shear thickening mean? Means that like if we see this equation, okay, so we can see here, as we increase your this strain rate, okay, shear strain, then what is happening, then we can say if we increase this value, and since for dilatant your N is greater than equal to 1, so this value will be positive, and if we increase this value, increase the strain, your apparent viscosity increases. So your like fluid is thickening with the respect to your strain. Okay, the larger the strain, the higher the thickness of the fluid. Okay, now there are certain examples of this. So example, if we talk about, so then the famous examples are sugar solutions, then your quicksand, and we can also talk about starch solutions, solution, etc. Okay, so these three examples are for your dilatant. Next, let's talk about your pseudoplastic. Pseudoplastics. Okay, so this pseudoplastic is like similar opposite to your dilatant fluid. This is your shear thinning fluid. Shear thinning fluid. Okay, and if we talk about example, so example will include your blood, milk. Okay, and we can also talk about lipstick. Okay, next let's talk about your okay, so Newtonian fluids. Third is your Newtonian fluids. Okay, so according to Newtonian fluids, like as I mentioned in your dilatant and pseudoplastic, your shear, these are your shear, like your viscosity will keep on changing. Okay, but in case of your Newtonian, as N is equal to 1, so if we put N is equal to 1 here, So we will see that this term will become constant, that is A. Okay, so here we will write that for Newtonian fluids, viscosity remains constant. Viscosity remains constant. Okay, and your Newton's law of viscosity is Newton's law of viscosity. Law of viscosity is for uh, Newtonians only. Newtonian fluids only. Okay, Newtonian fluids only. Okay, and if I want to talk about the examples, then your general items like water, air, alcohol. So these are some examples of your Newtonian fluids. Okay, now we are left with your Bingham plastic, thixotrope, and rheopectic. So these are your, like in these cases your B is not equal to 0. Okay, so let's talk about, okay, so let me write Bingham plastic here only. What one is your Bingham plastic? Bingham plastic. Okay, so Bingham plastic is, this violates basic deformation of fluids. Basic deformation of fluids. Okay, so only after certain stress application does your deformation take place. Okay, so example for Bingham plastic are your toothpaste, gels, etc. Okay, gel, etc. Okay, now if we talk about your next one, fifth, that is your rheopectic. Let's talk about rheopectic. So rheopectics, for rheopectic your mu viscosity increases with time. Okay, and example for rheopectic are printer ink, gypsum, plaster, etc. Okay, if we talk about your sixth one, that is your thixotropic. Okay, so in case of thixotropic, your mu decreases with time. Okay, and examples are bentonic fluids. Okay, now there is a special type of fluid that is known as your viscoelastic fluid. That is your viscoelastic fluids. Okay, so viscoelastic fluids are fluids which after some deformation partially, like what happens solids in solid, after deformation your solid regains its shape. Okay, but in case of your viscoelastic fluid, it partially returns to its original form. Okay, after some deformation, of course on removal of load. Okay, and example for viscoelastic are some special type of polymers. Special polymers are example for your viscoelastic. So now, since we are done with your theory work, we will start our questions. So this is your question number 1. This question states that a block of weight W, this slides down on an inclined plane while lubricated by a thin film of oil. Okay, the film contact area is A, and its thickness is H. Okay, assuming a linear velocity distribution, so we have to like assume that velocity distribution is linear. Okay, sorry, like this. So your velocity is V at this point and 0 at bottom, because bottom is contact layer. Okay, like this linear velocity profile, linear velocity distribution in the film, derive the expression of terminal velocity, terminal or zero acceleration. Okay, so we know that since this weight W will act in downward direction like this. Okay, and we can like make it into two components. This is your W cos theta, and this component here is your W sin theta. Okay, so and of course like this shear stress will be acting on this plane backward direction. Okay, shear force will be acting on backward direction. Okay, so we know that shear stress due to your linear velocity profile is given by mu times of V by H. Okay, and so we can write your shear force Fs is equal to like tau into area, tau into area, and area of contact given as A only. Okay, so this is mu V A by H is your shear force. Okay, this is your shear force. Okay, now your downward force is W sin theta. So what we can do, we can write for zero acceleration, zero acceleration, what should happen? Your like net force should be 0. Summation of F should be equal to 0. So your W sin theta is in like this direction and WFS in direction. So W sin theta minus Fs should be equal to 0. Okay, so if we substitute the values, so we will obtain W sin theta is equal to your mu VA by H. So from here we can write V is equal to WH sin theta by mu times of area. Okay, so this is your terminal velocity. Okay, terminal velocity. Okay, so I hope you understood this question well. Okay, now we will move into our next question. So in this question it is mentioned that a shaft of 6 centimeter in diameter is being pushed axially through a bearing sleeve of 6.02 centimeter in diameter. Okay, so we have a bearing sleeve. So let's say this is your bearing sleeve here, and this is your bearing. Okay, this is your bearing sleeve, and this gap between these 2 points is your 6.02 is your 6.02 centimeter. Okay, as mentioned here, this is your diameter. Okay, and we have a like your shaft inside of diameter 6 mm. Okay, so let's say this is your shaft. Okay, so this is a shaft, and this shaft will be exactly in middle. Okay, so of course there will be certain gap between these. Okay, and between the shaft and the bearing, we know that we have okay, one more thing before that, like this shaft should be larger in size. Okay, one more thing, let me correct it. correct this for a while. Okay, let this is your sleeve. Okay, so this sleeve, between this sleeve we have a shaft. So this is your sleeve. Okay, and this between is your shaft, and the size of the shaft is, diameter is 6 centimeter. Okay, and it is given at 40 centimeter long. Shaft is through bearing sleeve. Okay, so it is pushed through. Okay, so this is, let's say, 40 centimeter. 40 centimeter. Okay, the clearance, assume the clearance, assume uniform. Okay, so the clearance, we can say that this clearance, let's say it as h. Okay, h, so we can write h is equal to 6.02 minus 6 divided by 2, that is your 0.01 centimeter. Okay, and your velocity with which your shaft is being pulled, velocity with which your shaft is being pulled is given as your 0.003 meter per second. Sorry, this is mu. Okay, so velocity is 0.4 meter per second. 0.4 meter per second with your specific gravity is given. So we can write your density of the fluid is equal to 880 kg per meter cube. Okay, and your nu is given as 0.003 meter square per second. Okay, and we can write this as 0.001 or in meter. Okay, sorry, this is 10 to the power minus 4 meter. Okay, 10 to the power minus 2 centimeter, and to convert it in meter we have to multiply it by, right, 10 to the power minus 2 again. So this is your result. Okay, now what I can do, like first I have to, it is asked the force required to pull the shaft. Okay, so let's say that F is the force applied. Okay, so force F, we can write it as like your shear force, amount of shear stress into area. Okay, now we can write shear stress, as shear stress value we can write it as mu V by H again. Okay, as like we can, since the sleeve is very small, sleeve gap is very small, so we can assume it to be linear in times of area. Now area of contact will be in circular type. Okay, this whole area will be in the contact. Okay, so pi times of area will be pi d, pi times of diameter d of shaft. Okay, because shaft is moving with your velocity v. Okay, now if we substitute the values here, and one, sorry, pi d is your perimeter into your like length of the shaft. Okay, L shaft. Okay, so if we substitute the values here, so we can write mu is equal to rho times of nu, rho times of nu. Okay, or let me calculate it differently here. So we can write mu is equal to rho times of nu. If we like multiply this both terms, so we will obtain 8 3s are 24. So this will be your like 2 decimal places 2.64. Okay, this is your Pascal second. So if we substitute the values here, 2.64 into velocity, velocity is given as 0.4 meter per second divided by h, h is your 10 to the power minus 4 meters. Okay, always like keep your attention on units. Okay, you shouldn't mess with them. Okay, your answer will be like far from dry. Pi into d shaft, d shaft is your 6 centimeter, 6 centimeter is 6 into 10 to the power minus 2. Okay, and the length of shaft is 40 centimeter, so 40 into 10 to the power minus 2. Okay, now these terms can be cancelled out. Okay, So if we solve this, so we will obtain force F will be equal to, or let me write it with this pen only. So force F required will be equal to your 2.64 into 0.4. So 2.64 into 0.4 into pi, that is 3.142 into let's say 6 into 40. So this turns out to be 796.3. This is in your Newton. Okay, so this amount of force will be required to push out your shaft from this sleeve. Okay, and one more thing, this is pushed, okay, not pulled. The arrow should be on this side. This is your push. Okay, so I hope you understood this principle well. Okay, so we have to calculate your shear stress, and you have to keep in mind what is your area of contact. Okay, this A is your area of contact. Okay, so now let's look into at next question. So it is mentioned that a disk of radius r operates at an angular velocity omega inside a disk type container filled with oil of viscosity mu. Assume a linear velocity profile and calculate the shear stress on the outer disk edge. Derive a relative formula for viscous torque on the disk. Okay, so we have to calculate the torque on the disk. Okay, so let's see what will happen. So if this disk will rotate, okay, this disk is rotating, so a velocity profile will be formed. Okay, and here there will be some velocity. Okay, and velocity at this point is 0. Okay, and as we move further from the center, so the larger the velocity will be. Okay, and this velocity will be equal to r times of omega, r times of omega, like it is mentioned by ohm here. Okay, okay, and here there will be different r, here there will be different r. Okay, and this profile will form on both edges, both sides. Okay, so its shear stress will act this end also, and this point, this both side, on both sides your shear stress will act. So what we will do, we will at a distance r from the center, let's say this is your distance, small r, we will consider an element. Let's consider this element. Okay, and this element have your thickness of dr. Okay, and what we will do, we will if I draw velocity profile at this point, so velocity profile at this point, so this will be equal to your r omega, this v will be r omega, and of course like this. Okay, okay, this will be like this, and of course on both ends, on both sides. Okay, on both sides. Okay, this is something like this. Okay, so we can write that tau at r location, will be equal to your mu times of v by h. Okay, we know that tau is equal to mu times of v by h, but here since it is acting like both up and down side, so we will use 2 times of mu v by h. Okay, and your this will be 2 times of mu times of v. Now if we talk about v will be your r times of omega, not omega, this is like this. Okay, okay, r omega by h is given as clearance. Okay, okay, this is your tau r, shear stress at any point. Okay, now if I talk about the small shear force element that is acting on like the disk, like if this is a disk, so it will act in a circular manner, na? So this element will be considered in this circular manner. This complete will be element if we consider in this plane. Okay, I hope you understood this point. Okay, so your DFS will be equal to tau r into dA, that is area of contact, small area of contact, elemental area of contact. Or okay, so this will be equal to your 2 mu times of r omega by h times of dA. If we talk about dA, so like the circumference will be 2 pi r times of dr will be, if you multiply with dr, so this will be your dA. Okay, and here we have been asked to to calculate your viscous torque. So if I talk about torque dt, okay, torque at radius r, so r will be given by dfs or let's say it is a dt only, so dfs into r. At a distance r it is acting na, so dfs into r. So if we write this, so we will obtain it as equal to, or let me write it here only, this will be 2 times of mu omega by h into 2 pi times of r cube dr. So this is your like this is what we obtain here. Okay, so this r we have, this is r square, and here one more r, this is r cube times of dr. Okay, so if I want to calculate your total torque, so to calculate total torque we have to like integrate this term. So let's integrate this term from let's integrate this term from your 0 to capital R. From r is equal to 0 to r is equal to capital R. Okay, so if we do this, so we will obtain our torque T is equal to, so this will become your 4 pi mu omega by h times of your, this r cube will be r की power 4 by 4. Okay, and limit is from 0 to r. Okay, so your torque I can write it as equal to pi mu ohm r की power 4 upon h. Okay, so I hope you understood this solution. Okay, you get how to like consider your how to calculate your small elemental force, and then to continue calculate your torque. Okay, and why we I think you get that we, to calculate torque we have to calculate elemental torque first, because torque varies from like with radius your torque will vary. Okay, so we have to calculate your elemental torque only first. Okay, now we will be moving to our next question. Now next question, this is your next question. So a solid cone of angle 2 theta, base radius r naught, and density rho c is rotating with initial velocity omega naught inside a conical seat. Okay, the clearance h is filled with the oil viscosity mu. Okay, neglecting the air drag, derive an analytical expression for the cone angular velocity omega t if there is no applied torque. Okay, so we have been given the initial angular velocity of omega naught. Okay, initial angular velocity of omega naught, and like since there is no applied torque, so what will happen due to the presence of fluid, due to the shear presence of shear force. Okay, what will happen, your speed will keep on decreasing. Okay, so you have to like calculate the omega t. Okay, and expression for omega with respect to time. Okay, so let's start this. So in this question again, like since we can say that with the central axis, so this is your central axis, so with respect to your central axis your r is varying, radius is varying. Okay, so let's take distance h from the base here. Let's say this distance. Okay, let's say this distance is your y. Okay, so at a distance y from the base from this apex of the cone. Okay, we are taking this radius that is r, okay, and let's take up to height of your dy. Let's say this is your dy width. Okay, and here again your radius will be r only. Okay, and this is your contact length. Okay, this is your contact length. And velocity distribution at this point, let's say it to be this. This is your velocity distribution. Okay, so we can write that tau at y radius is equal to mu times of v. V is your r times of omega divided by h. Okay. Okay. Now here your unknown is r. Okay. So from similar angle, let's say that this angle is theta. Okay. So we can write, and one more thing, let me mention it here. Let's say that this length here, total length, let's say that is capital L. Okay. And this small length is small l, and this increment is, let's say, dl. Okay. So we can write that this cos theta, if I want to write, let's say, sin theta is equal to perpendicular upon hypotenuse, so I can write it as r naught by l. Okay. And cos theta is equal to r naught by, let's say, this is your distance, let's say this complete distance is your capital Y. Okay. So r naught by y. Okay. So from here I can write or we can leave this with respect to this perpendicular line, and let's move according to this one here only. Okay. So sin theta is equal to r naught by l. So from here we can write that my l is equal to, or I can also write this is equal to, is equal to r by l. Okay. Small l. This should be your small l. Okay. Now what I can write? I can write from here that r is equal to l sin theta. Okay. So we can also write that dr is equal to dl sin theta. Okay. And this distance here is your dl. Okay. So I can write this tau is equal to mu times of r. I can write it as l sin theta. L sin theta times of omega divided by h. Okay. And if I want to, let's say, write a small unit force on this element, and this element will be in your circle. Okay, like this. Okay, all around. So if I want to write unit force, so I can write it as elemental force, so I can write it as tau I times of dA. Okay. And your tau I is given by mu times of L sin theta by omega divided by h. Okay, times of dA. Now dA here will be your 2 pi r is your, okay, let me write dA here only. So I can write my dA is equal to 2 pi r times of dl, because dl is this slight length. Okay, perimeter times of length is your area. If I substitute the value of r, so I can write 2 pi sin theta into ldl. Okay. So let's write it here. 2 pi sin theta into L dl. Okay. Now if I want to calculate the torque, so I can write dt is equal to r times of dfs. Okay. And I think it would have been better if we have been proceeding with r only. Okay. So let me do it here for easier calculation and not so much misconception like we have here. So this is your mu r omega by h times of dA is your 2 pi r times of dl. 2 pi r times of dl. Okay. Now we'll multiply it by r again. So this will be mu okay, or 2 pi mu w by h times of your, this is r into r square, and this is again r cube times of dl. Okay, so we can write, like you can write your r as L sine theta. Okay. So let's write it as, so we can write it as, let me write it in next line. So dt is equal to 2 pi mu omega by h. Okay, now if we do r cube, so it will be L cube sine theta cube. So sine cube theta times of L cube dl. Okay, now we can integrate it, and the integration should be from your L. Now L is equal to 0 to capital L, 0 to capital L. Okay, so if we do this, so we will obtain our torque is equal to 2 pi mu w omega sine cube theta. Now this will be your L ki power 4. Okay, so and if we apply the limit, so this will become L ki power 4 divided by 2 times of h. Okay, so this will be like upon 4, so twice 2 to the 4, so this will be 2h, like this. Okay, so this is your torque. Now if we substitute the value of L, we can write it as r naught by sine theta. Okay, so we will obtain pi mu omega times of, now L we can put it r naught by sine theta, so this will become r naught or small r naught की power 4 divided by 2h sine theta. Now since we have given the value of initial angular velocity omega naught, okay, and we have to calculate the final angular velocity, so we can move to your angular momentum theorem. Okay, so we know that we can write our t is equal to I times of d omega by dt. Okay, now for this cone, we know that for cone we write I is equal to I along this central axis is equal to 3 by 10 m r naught square. Okay, now you can also derive this formula for moment of inertia. Okay, m mass moment of inertia, this is basically. Okay, so from here, and we have been given that base radius is r naught and density is rho c, so we can write I is equal to 3 by 10 times of volume. Okay, so volume of cube we know is equal to, rho times of volume is mass, rho c is the rho of cone, volume is 1 by 3 pi r square L. Okay, so pi r naught square times of L. Okay, now this is your mass times of r naught square. Okay, so I can write it as equal to pi rho c r naught to the power I can substitute L is equal to r naught by sine theta here also. Okay, so this will become r naught to the power 5. Okay, divided by 10 times of this will become your sine theta will be left here. Okay, this is I. Okay, and let's say I want to now I want to calculate your omega t value. Okay, So how will I calculate this? So I will substitute these values here. So this torque will act as like your braking your will like your decrease the angular momentum of the system. Okay, so if I equate both of them, so this is basically your resisting torque or braking torque. So I will write here in negative, write it here in negative. So this I can write it as minus pi mu omega r naught to the power 4 upon 2h sin theta is equal to I, that is your pi rho c r naught to the power 5 r naught to the power 5 upon 10 sin theta. Okay, sorry, like your this is not L. Okay, that is your pi RL is your surface area. This is your 1/3 pi r naught square type of height. This is your height. Let's say this is your capital H height. Okay, and we can write from here that like tan theta is equal to r naught by h. R naught by h. So h is equal to r naught by tan theta. So this will be your tan theta here. Okay, by tan theta. Okay, so here again we will write tan theta times of d omega by dt, d omega by dt. Now the various term will cancel out. This from this, pi from pi. Now 2 5s are 10. Okay, so here what we will obtain? We will obtain mu, of course, negative of mu omega. Now again from here, like let's take 5 also here, 5 mu omega times of 5 mu omega. Now this tan theta is equal to sin theta upon cos theta. So this will become 5 mu omega upon 5 mu omega upon h cos theta times of rho c r naught is equal to d omega by dt. So let's write dt here and omega here, and now we will integrate both side. Okay, so from omega node to omega of t. Okay, and here variation is time. So from time t is equal to 0 to time tt. Okay, so from here we will obtain our ln of omega t by omega node is equal to from here this will be 5 minus 5 mu, or we can write it as equal to your mu t is equal to omega naught times of exponential of minus 5 mu by h rho c r naught cos theta times of t. Okay, so this is your expression we have to calculate. Okay, this was a lengthy one. I hope you understood here. Okay, now we will be moving to our next question. So this is your next question. A device in the figure is a cone plate viscometer. The angle of cone is very small, so this angle theta is very small here. So that sin theta is equal to theta, and the gap is filled with test liquid. The torque M to rotate the cone at the rate of omega or ohm is measured. Okay, find the linear velocity profile in the assuming the linear velocity profile. Derive the expression for viscosity for the fluid viscosity. Okay, so this should be mu. Okay, mu as the function of mr, omega, and theta. Okay, so again, like here we have varying height, varying h. Okay, film thickness, we have been varying film thickness with r radius. Okay, so let's say at this radius r we have film thickness, that is your, let's say this is your y. Okay, and here at the end, let's say it is h. Okay, so from here, similar triangle, we can write y upon r is equal to h upon capital R. Okay, and this is also your, like if we consider this as theta, so theta is equal to perpendicular upon base is equal to tan theta. I hope you understood till here. Okay, okay, so we can write y is equal to r tan theta. Okay, so we can write that my tau shear stress value is equal to mu times of v by h, like your formula is v by h. So v here is your r times of omega divided by h. H is your here y. Okay, and your y is equal to r tan theta, so this will be mu ohm by tan theta. So this is your tau. Okay, shear stress at this r. Okay, and of course we have been taking in elemental fluid here. Okay, and this is your dr. Okay, so to calculate the small elemental force dfs, we use tau into dA, and this is equal to mu ohm by tan theta by dA into dA. So dA is your 2 pi r times of dr. Okay, now to calculate torque, as it is mentioned here, fluid viscosity mu as a function of, okay, so our small torque dt will be given by dfs into r is equal to mu ohm into 2 pi by tan theta into r square dr. Okay, and we can calculate, like integrate this to calculate our torque, and integration is from 0 to capital R. So if we solve this, so we will obtain my torque, or let's say moment, from 0 to m, moment m as it is mentioned here. Okay, torque m. Okay, so m is equal to your 2 pi, or here it will be r cube by 3, so 2 by 3 pi mu ohm by tan theta times of r cube. Okay, so this is a moment. Now if I want to calculate the mu, that is dynamic viscosity as it is mentioned here, what is the fluid viscosity mu? So mu is equal to your, it will come out to be 3 by 2 times of m tan theta divided by pi omega r cube. Okay, so this is your final answer. And one more thing here, it is mentioned that sin theta is similar to theta. So our tan theta we can also write similar to theta. So we can write it as your mu is equal to 3 by 2 m times of theta divided by pi rho ohm r cube. Okay, okay, so this is also your correct one, and we have to like do this. Okay, because it is mentioned already in the question that sin theta is similar to theta. Now moving to next question. Thin plate is separated from two fixed plates by a very viscous liquid mu1. and mu2. Okay, the plate spacing h1 and h2 are unequal as shown. The contact area is A between the center plate and each fluid. Okay, assume the linear velocity distribution in each fluid. So in this fluid, the linear distribution would be like this. Okay, and this velocity would be V as mentioned here. Okay, this is the velocity distribution. Here also, similarly, this will be your velocity distribution. Okay, this is the velocity distribution. Okay, and assuming the linear velocity distribution, drive the force F required to pull the plate at velocity V. Okay, so due to this velocity profile, a shear stress will be acting, and we know that shear stress in this case will be constant. Okay, and this is your shear stress distribution. Okay, although we don't need here. Now let me write. We can write your we know that tau is equal to mu times of V by H. Okay, so if I talk about small like force, shear force on the plate, so Fs, this should be equal to your 2 times of tau into area, like tau here, tau, and this tau times of surface area as mentioned, A, contact area A. Okay, now this can be written as 2 mu V A by H. Okay, so this is your shear force, and for equilibrium we will write for equilibrium our Fs should be equal to your F. Okay, like for okay, like for linear for simple velocity. Okay, like for due to for presence of no acceleration present. Okay, so we can write our A part answer, that is, so this is your basically A part we are considering from here only. Okay, so your F force required is equal to 2 mu VA by H. Okay, and B part, it is asked that is there a necessary relation between two viscosities. Okay, sorry about that, my bad. So this is your viscosity mu1 and height h, to both are different. Okay, so let me do it here now again correctly. So this would be written as mu1 times of V times of h1 plus mu2 times of V by h2. Okay, now this will be your mu1 V A or mu1 by h1, mu1 by h1 plus mu2 by h2 times of your V times of A. Okay, now Fs is equal to F, so we can write from here that F is equal to mu1 by h1 plus mu2 by h2 times of V times of A. So this is your total force required to like pull the plate at a velocity V. Okay, now second part, is it there a necessary relation between two viscosities mu1 and mu2? So while we're doing this, so we can also write like this tau as here Fs1 shear force 1, and here it is Fs2. Okay, so Fs is equal to, this will be basically our Fs1 plus Fs2. Okay, so if we see this, so we can see that these two are different summation of tau A. Okay, or tau times of A. Okay, so these two are independent shear forces. Okay, so these two are not dependent on each other, and this f is simply the sum of fs1 and fs2. So for B part, is there necessary relation between two viscosity mu1 and mu2? So no, there is no relation between both of these. Okay, because both forces fs1 and fs2 depend individually on their own viscosities only. Okay, so I hope you understood this solution. Now moving to next question. A thin 30 centimeter by 30 centimeter flat plate is pulled at 3 meter per second horizontally through 3.6 mm thick oil layer sandwiched between two plates. One is stationary and another moving at a constant velocity of 0.3 meter per second. Okay, so this is moving in backward direction. As shown in the figure, the dynamic viscosity of oil is this. Okay, so mu is given as this. Assume the velocity in each layer to be very linearly. Plot the velocity profile and find the location where oil velocity is 0. Determine the force that needs to be applied on the plate to maintain this motion. Okay, so like if we look at the above surface, like upper section, so here we can say that since it is a fixed wall, so velocity here would be 0, and this plate have the velocity of 3 meter per second in this direction, so it should be something like this. Okay, and this velocity is your v here. Okay, so it is like this. Now but this is the lower plate, lower region we can see that this plate is moving in backward direction at a speed of 0.3 meter per second. So if I like draw it graphically, so graphically this point here, like velocity will be in this direction, and this is your VW, V of wall, moving wall. Okay, so it should be like this, joined like this. Okay, and this is your asked for to plot the velocity profile, so this is your velocity profile. Okay, and find the location where the oil velocity is 0. So at this point your oil velocity is 0. Okay, and let's say that this is at a distance y from the bottom plate, moving wall. Okay, so how can we calculate y? Using similar triangle, using between this triangle and between this triangle. Between these two triangles we will apply your similar triangle principle. Okay, so what we can write? We can write using similar triangle principle. We can write what we can write. We can write that VW by y is equal to this velocity v divided by h2 minus y. Okay, so if we substitute the values here, so it will become like this: 0.3 divided by y is equal to v, velocity is 3, divided by h2 minus y. So h2 is 2.6 mm. So if we keep this in mm, so we will obtain our y in mm only. Okay, so so if we solve this, so we will obtain it as 2.6 minus y is equal to 10y, because like if we remove the decimal place here, so here we will obtain 10. This is 10y and this is 2.6 minus y. So from here we have obtained our y to be 2.6 divided by 11, that is equal to, let me calculate it. So this will come out to be your y is equal to 2.363 mm. Okay, so this is your answer, and this distance is from your moving wall, from moving wall. Okay, now in B part, it is asked to determine the force that needs to be applied on the plate to maintain this motion. Okay, so the force, if we talk about the force F, then that will be equal to like shear force on this Fs1 plus Fs2 is equal to Fs1 plus Fs2. Okay, now this force F will be written as Fs1 if I want to write, so I can write mu1. Okay, let's see. So mu1 is equal to mu2 is equal to 0.027. Okay, so mu times of V. Now this is VV, this V, okay, divided by H, and this H is H1 plus Fs2. So here for Fs2, if I want to write, let's say, write your velocity in this region. So if I should like talk about relative velocity here. Okay, so relative velocity will be this velocity minus this velocity. So this is your V minus, now this VW is in opposite direction, so V minus of minus VW. Okay, divided by height is your H2. Okay, okay, and of course I forgot about area A. Area A, this is a shear stress into area A. So area A will be equal to, so it is given 30 centimeter by 30 centimeter. So this is your 0.3 into 0.3 is equal to 0.09 meter square. 0.09 meter square. This is your area. Okay. Now if I substitute the values here, so you will obtain F is equal to mu times. So mu is your 0.027 times of, let's take A common 2. Here also it will be mu. Okay. So A is our 0.09 times of here V. V is our 3 divided by H1. So since we have like considered this V in meter only, so let's take H1 and H2 in meter also. So 1 meter, 1 mm is your test for minus 3 meter. Okay, plus now here V minus VW. So V is our 3 minus of 0.3, so 3 plus 0.3 divided by, now your H2 is 2.6 mm, so 2.6 into 10 to the minus 3. Okay, so this is your value of H2. Okay, so if we solve this, so we will obtain our value, that is your this value will become, so this will be your equal to F equal to 10.37 Newton. Okay, so we have obtained our force required to pull in second part is equal to 10.37 Newton. Okay, so with this we have completed our this question. So you have to like keep an eye on these type of questions. Okay, when like your both surfaces are moving, if both surfaces are moving, so to calculate your shear stress, you have to consider relative velocity here. Okay, relative velocity of sit on the plate, on like the plate which you should consider is stationary. So after that you can calculate the relative motion of your actual like on which we have to do calculations with respect to moving wall. Okay, so now moving to next question. So it is observed that density of ideal gas increases by 10% when compressed isothermally from 10 atmosphere to 11 atmosphere. Determine the percentage increase in density of the gas if it is compressed isothermally from 1000 atmosphere to 1001 atmosphere. Okay, so we know that we can represent your isothermal or bulk modulus K is given by dP upon or we can write minus V dP upon dV, or it can be written as rho dP by d rho. Okay, now what is given here? It is given that for a ideal gas, your d rho by rho is equal to 0.1. Okay, and for your corresponding this temperature, this pressure difference, and for delta P or dP is equal to 1 atm. 1 atm. Okay, and 1 atmosphere is given by 101.325 kilopascal, or let's keep in terms of atmosphere only. Okay, so from here I can write the value of bulk modulus is rho d rho is equal to your dp1 upon 0.1 is equal to 10 atmosphere, 10 atm. Okay, now we have to calculate the percent decrease in density, increase in the density of the gas if it is compressed isothermally from 1000 atmosphere to 1001 atmosphere. Okay, so it is again the pressure difference is delta V. So from 1000 atm to 1001 atm, your delta P is equal to 1 atm only. Okay, so using this, so I can write K is equal to delta P upon d rho by rho. Okay, so from here I can calculate d rho by rho is equal to delta P by K. So delta P is our 1 by K is our 10 atm, both are in atm. This is again 0.1, so this will be equal to 10%. So from here we can say that the percentage increase in density of the gas if it is compressed from isothermally from 1000 atm to 1001 atm is same as that of in case of your compression from 10 atm to 11 atm. Okay, I hope you understood this point well. Okay, now we will move to next question. A spherical water drop of 1 mm in diameter splits up into 64 smaller drops of equal size. The surface tension coefficient of the water is this. The work required to splitting the drop is. Okay, so we know that surface energy or work done, surface energy or work done is equal to sigma times of total change in area. Total change in area. Okay, so it is mentioned that a spherical droplet of originally it was of 1 mm in diameter, splits into 64 smaller droplets. Okay, so the volume initial is equal to volume final. Okay, let's say that small r is the final radius, or small d or d2 is the final or smaller drop diameter. Okay, and so I can write volume is equal to pi by 6 d cube, pi by 6 into 1 cube. Okay, initial volume is equal to final volume is equal to pi by 6 into d2 cube. Now this is your 64 droplets, 64 similar droplets are there. Okay, so it should be like this. So from here I can write your d2 cube is equal to 1 upon 64. Okay, so from here we can write d2 is equal to 1 upon 4, cube root of 64 is 4, and this can be written as 0.25 mm. Okay, so this is your d2. Okay, now the work done, if I want to write work done, so I will have to calculate the change in surface area. Okay, so delta A, if I want to calculate, so this will be your final surface area minus initial surface area. Okay, so or we can calculate the area initial is equal to, will be your, like, since it is spherical in shape, so this will be pi into pi d square. Okay, pi d square is equal to pi mm square. Okay, now area final, if I talk about, final is equal to 64 into pi into d square. So pi d square is 0.25 square, so this will be equal to 4 pi mm square. Okay, so I can say that work done is equal to surface tension sigma into dA, that is A final minus A initial. तो पढ़ नहीं रहा ना, बिल्कुल छोड़ दिया ना. So from here if we substitute the values here, so sigma is equal to 0.073 times of area final is 4 pi minus initial area is pi. So this is your 0.073 into 3 pi. Okay, so we know that pi is equal to 3.142, so let's multiply it, 3 into 3.142 into 0.073. So we obtained value to be, so work done is equal to, okay, and one more thing, so this is in your mm square. Okay, so let's convert it into your meters. So in meter, this will be your area is 4 pi minus pi into 10 to the power minus 6 meter square. Okay, into 10 to the power minus 6 meter square. Okay, so 6.88 into 10 to the power minus 7 joules. Okay, this is your work done to, like, break the liquid droplet of 1 mm diameter into 64 pieces. Okay, now moving to next question. So consider 0.15 mm diameter air bubble in a liquid. Determine the pressure difference between the inside and outside of the air bubble if the surface tension at the air liquid interface is this. Okay, so this is mentioned about air bubble in a liquid. Okay, so inside a liquid we have air bubble. Okay, so this is your one interface system only, one interface. So for one interface we can write your delta P is equal to sigma times of, or 1 sigma times of 1 by r plus 1 by r. Okay, is equal to 2 sigma by r is equal to 4 sigma by d. Okay, so we will substitute the values here. So 4 times of sigma is 0.08. Okay, divided by diameter. Diameter is, like, this in meter, so let's take this in meter also. So this is your 0.15 times of 10 to the power minus 3. Okay, so if we solve this, so this will be 2 divided by 15 is 2.13. Sorry, and this is your 2.13 kilo Pascal. Okay, this is your answer. Okay, okay, Now moving to the next question, the surface tension of the liquid to be measured using a liquid film suspended in U shape on the U-shaped wire frame with 8-inch long mobile. Okay, so the wire shape is something like this. Okay, U-shaped. Okay, or we can, like, I can draw it like this. So wire is like shaped like this. Okay, and it has a movable wire frame 8 centimeter long. So this is like this, something like this. Okay, and this is your 8 centimeter. This from here to here is your 8 centimeter. Okay, let's say this to be capital B. If the force needed to move the wire is, now to move the wire we need a force F equal to your 0.024 Newton. Okay, determine the surface tension of the liquid in the air. Okay, so this wire does have some diameter. Okay, so we will consider the surface tension of both upper side and lower side. Okay, so this force should be considered to be equal to your surface tension force. Okay, so this force is equal to your 0.024, okay, Newton, and the surface tension force is your sigma, that is surface tension value, which we have to calculate, okay, into your length of the action. Okay, so this length of action will be, should be your 2 times of B. Okay, and 2 times of B, why is, because like B dimension this one in like both upper side and lower side of the smaller wire. Okay, so this from here, if we substitute the value, so this will be your sigma times of 2 times of B is your 8 centimeter, it is 0.08 meter. Okay, so if we divide 0.024 divided by 0.08, we will obtain is equal to your 0.3. So sigma is equal to point. Okay, sorry, I forgot to divide it by 2 also. So this will be 0.15 Newton per meter. Okay. Okay. So this is your surface tension. Okay, now moving to the next question. A cylindrical shaped solid needle made of steel having density this is is floating in the water, which is 20 degrees Celsius, having density of 1000 kg per meter cube. The surface tension of the water air interface is this. Assume that a contact angle is 0 degree. The maximum diameter of the needle would be. Okay, so let's consider container. Okay, so let's say this is your surface of the container. Okay, sorry, surface of the free liquid surface. Let's say this is your free liquid surface. Okay, it's something like this. Copy and then paste. So let's say this is your container. Okay, and this container is filled by some liquid. This container is filled by some liquid. Okay, and this is your free surface of the liquid. Okay, this is your free surface of the liquid. This here is your free surface of the liquid. Okay, and we have placed a needle. This is a needle. Let's say this is your needle. Okay, this is a needle that is placed on the water. So due to like if needle is placed, so your surface tension will act. Okay, surface tension will act. Okay, and like let's say this is your theta angle, angle of contact. Okay, so it is mentioned that take the contact angle to be 0 degrees here. Okay, so from here what we can see that the weight of the wire will be acting in downward direction. Okay, weight of the wire will be acting in downward direction. Sorry, contact angle should not be this, it should be this one angle. Okay, this angle is let's say theta. Okay, so we can say, so okay, sorry, this angle is theta. Okay, so we can say that W, weight of needle is equal to upward surface tension force component on needle. Okay, so your weight of the needle is given by W, that is your rho V, rho times of volume times of ascertained gravity G. This should be equal to this. So this is your sigma times of cos theta is your upward component of your surface tension times of length. Length of contact is 2 times of length of the needle. Okay. Now it is mentioned that the cylindrical shaped needle is made of steel having density of 8,000 kg per meter cube floating in the water, which is this. And okay, so maximum diameter of the needle would be, okay, so diameter of the needle we have to calculate. So diameter of needle we can calculate by using V. So V, we can write volume of the needle to be pi by 4 d square into L into G is your 9.81, we can use this, okay, is equal to sigma is given as your 0.073 into cos theta. Since theta is mentioned to be 0 degree, take it is equal to cos theta will be our 2 times of L. Okay, now this L and L will cancel out. So from here we can like cancel this out. 2 4 to the 8 and this will become 1000. Okay, so let's solve the 0.073 divide by 9.81 divide by pi, that is 3.142 divided by 1000. Okay, and if you want to like do square root of this term, so it will be power 0.5. So this square root will become d is equal to your in mm if I want to write, so this is 1.5 mm is the maximum diameter that it could take. Okay, like we can write it as like weight of the needle should be less than equal to upward tension force. Okay, we can write it like this. Okay, so from here we have obtained that d should be less than equal to 1.54 mm. Okay, so I can less than 1.54, so I can write d max is equal to 1.53 mm. Okay, so if I want to like take it to one decimal place only, so I will directly write 1.5 mm. Now a capillary tube internal diameter 2 mm is immersed in a pool of water to a depth of 1.15 mm. Okay, so there is a water beaker. Let's say this is a container of water. So let's say this is your filled up to this level. Okay, now it is mentioned that capillary tube is dipped inside this. So let's say that this is your capillary tube. Now it is mentioned that okay, sorry, this is a capillary tube, let's say. Okay, so this is your capillary tube. Now it is mentioned that it is immersed 15 mm. So let's say this is your H, that is, or so let's say H is equal to 15 mm in depth of 15 mm. If air bubble are intended to have a diameter of 2 mm and the okay, so air bubble is formed using this capillary at this point only. Okay, this is your air bubble. Okay, so does have D is equal to 2 mm, and this air bubble also have D is equal to 2 mm. Okay, air bubble is intended to have a diameter of 2 mm, and the surface tension of the water is this. The pressure required okay, so we are blowing this question incomplete somehow. So we are blowing air into this through this capillary tube, okay, and to form a air bubble. So let's say Pi is will be the pressure which we will be like putting out from here, okay, and this will be our inside pressure of the bubble, okay. So we have to calculate that pressure only, the pressure which we have to supply, pressure at which we have to supply the air to form the bubble, okay. So we know that we can for single interface surface we can write delta P is equal to 4 sigma by D, okay. And if I calculate it, so 4 into 0.0725 divided by D is equal to 2 times of 10 to the power minus 3 is equal to 0.72.5. So 72.5 is 145. So this is your 145. Now this is your in Pascal, okay. 27 ja. Okay, so this is your dp, delta P is this, and now we know that delta P is P inside minus P outside is equal to 14.5 Pascal, okay. So we have to calculate Pi, and we know that P node is equal to P node, so 14.5 plus P node is equal to, we can write this to be here at this point your P node is equal to rho gh, okay, okay. So rho is your 1000 into g is 9.81 into h is your 15 mm, that is 15 into 10 to the power minus 3, okay. So if you solve this, so this will be 9.81 into 15, that is your 147.15 plus 14.5. So your the pressure required, that is Pi, will be 161.65 Pascal. I hope we are clear with this question. So there was to complete this question, pressure required to be blown, to be pressure required to blow air side capillary tube is dash Pascal, okay. So it should have in question, okay. Now let's move to next question. If the surface tension of the water in contact with air is this, okay, the correction needed to be applied toward capillary rise in manometer reading of the tube of 3 mm diameter. Okay, so let's say that in a pipe, so let's say this is the pipe and we have installed a manometer inside this, okay. So let's say this is a manometer, okay. So this is a manometer, okay. This is your manometer. Now the liquid filled inside this will be like rising to a height of, let's say, up to here only, here also, okay. So let's say this is your height h, okay, okay. This is your piezometer height, okay. But what is happening, that due to capillarity, what will happen? Your H capillary will be equal to 4 sigma cos theta by rho GD will be equal to 4 times of sigma. Sigma is your 0.075 into cos theta is cos 0 is 1 divided by rho G is 9810 into D is your 3 mm, that is 3 into 10 power minus 3. This is in meter. Okay, so this will be your 75 into 4 divided by 9810 divided by 3. Okay, so we have obtained H capillary is equal to 0.01019 meter, and this will be also be, you can write it as 10 point, this is similar to 10.2 mm. Okay, 10.2 mm. Okay, so so we can say that this actual actual height that that is measured, piezoelectric height that is measured will be equal to pressure. Let's say pressure at, let's say this is point A, so pressure at point A upon rho G, okay, plus H due to capillary effect. Okay, so this is your actual reading, this is your correct reading, this is your reading that is showing. Okay, so this is your incorrect reading, incorrect or reading showing. Okay, so this is your correction. Okay, so correction basically okay, so let me write it like this. Okay, so we write correction as correction is equal to correct minus incorrect. Okay, so correct one is your correct minus incorrect if I want to do, so this will be minus H capillary. H capillary is so correction required is minus 10.2 mm is correction. Okay, so this is your correction amount. Okay, so I hope you understood this question. So with this we are now done with your question section. Next session we will start our next chapter, that is pressure and its measurements. Thank you.